In this video, we are going to be talking about the washer method in terms of volume. So we saw that with this method, our region was adjacent to the axis of revolution. But what happens whenever it's not? So as you guys see in this diagram right here, whenever we rotate it, we're going to see a little washer right here, or a little donut, where we are going to have the radius of the outer function right here. We're going to do top minus bottom there. And then we're also going to do top minus bottom of the radius of the inner function right here. So the volume of the solid is going to be basically the volume of the outer function, so my furthest function, minus the volume of my inner function, which is going to be my function that is closest to my axis of revolution. Since we're still making circles right here, we're still going to do pi r square, but it's going to be a little bit different because we have the radius of the outer function, so top minus bottom of the outer function, so where it's furthest, and then top minus bottom of my inner function, aka which one is closest. All right, so looking at number one right here, we want to find the volume of the solid when y is equal to x, and y is equal to x squared is revolved about the x-axis. Notice how here, this is my x-axis, and my region is not adjacent to the x-axis. You see that there are gaps right here. Because we have a gap, that's going to create this little washer right here. Now, we are still going to do pi r square, and we're still going to do from 0 to 1 because that's my limits of integration right here. But we're going to do top minus bottom 2 times. We're going to do it for my furthest region first. So we're going to do top minus bottom here first. That is going to be x minus 0 square. And then I have my bottom, which is going to be my parabola. That's going to be x squared minus 0 squared dx. So this is my top, or my furthest function, so I do top minus bottom. And then this is my closest function, so I do top minus bottom here also. All right, I'm going to clean this up a little bit. I have the integral from 0 to 1 of x squared minus x to the 4th dx. I'm going to integrate this from 0 to 1. So then you get 1/3 minus 1/5. It's cubed. Obviously, if I were to plug in 0, that's not going to do anything because you have 0 minus 0, so nothing there. All right, number 2, we want to find the volume of the solid when y is equal to x, and y is equal to x squared is revolved around the line y is equal to 2 now. So we have the same function as number 1, except this time it is y is equal to 2. Now, if I were to look at this, I still have my region, my limits of integration being from 0 to 1. But if I were to think about my furthest function, that is going to be x squared now. And since I'm doing top minus bottom, I'm going to have 2 minus x squared minus, okay, and then my closest function. In this case, that's going to be my linear function. So that's going to be 2 minus x squared. Then I have dx. All right. At this point, once you have the set up, I'll be very happy. But of course, I'll be even happier if you give me the correct answer. So that's going to give me 4 minus 4x squared plus x to the 4th minus 4 minus 4x plus x squared dx. And then you're just going to simplify this make it pretty, and see what happens. So that cancels out. You're left with x to the fourth plus 4x. Let's see, x to the fourth, 4x, and then minus 6x squared dx. All right, if I did my math correctly, which I hope I did, you should get 8/15 pi as your answer. Yay. All right. So for number 1 and number 2, that was rotated about, let's say, the x-axis and y is equal to 2, where we did top minus bottom. You could do the same thing where we are going from right minus left. So we'll do a couple examples there. So looking at, let's say, number 3, we want to find the volume of the solid when y is equal to x squared and y is equal to 2x is revolved about the line x is equal to 2. Now, the problem with this is that we don't know where the intersections are. So we are going to go ahead and probably sketch this and see where it is. Okay. I know that was a bad graph, but you have the intersections there, so that's good. We have x squared is equal to 2x, x squared minus 2x. So, surprise, surprise, x is equal to 0 and x is equal to 2. Now, this is being revolved around the line x is equal to 2. So, it's this line right here. Now, because this is a vertical line, I can't really do top minus bottom here. Instead, I'm going to have to use right minus left. So instead of me using my bands of integration of 0 and 2, I'm going to use 0 and 4. The reason why I'm using 0 and 4 is because if I substitute n 0 and 2 into, let's say, this one right here, or this one right here, you're going to get 0 and 4 respectively. Okay, so we want to find my furthest function. In this case, my furthest function is going to be that linear function right here. I'm going to do right minus left, so I'm going to have 2 minus 2x. However, because this needs to be in terms of y, I have to solve for x. So that means that x is equal to y over 2 squared. So that is my furthest function. And then my closest function is going to be my parabola right here, my x squared. However, remember that since I need it in terms of y right here, that is going to be the square root of y. So I have right, which is going to be 2, minus my left, which is going to be the square root of y. And then dy. All right, it tells you to use a calculator for this, so I'm not going, oops, don't forget to put the square. I'm not going to ask you to take the antiderivative of this. It's possible, but it's going to get messy. But you should get 8/3 pi units cubed if you do it correctly. All right, you're doing the same thing for these types of problems right here, so I'm not going to do them. But essentially, if it's not adjacent to your axis of revolution, then you're essentially going to be using the washer method.